Okay, so yesterday we started talking about angles, and I had a couple of main goals yesterday in talking about angles. One of which was to basically begin reviewing what you know. And so before I even get to the slide here, let's just talk about some of the other things we did yesterday. So if I were to put a grid right here, if I were to put the angle like right here, is that how we would normally do that? Is that considered a standard position angle? Answer is no. I mean, even though you could probably guess that that's about, I don't know, 50 degrees perhaps, that's not how we traditionally try to draw an angle on a grid. We usually put it like right along the axis on one side, and then the other point has to start at the vertex. And so there's a triangle, and that maybe that has 50 degrees. So that was the first thing I wanted to remind you of. And that hopefully wasn't new. We can actually have angles that go like, say, from here down to like, say, there. And the way this works is this angle is actually going counterclockwise all the way around the circle, essentially. If I were to ask you to eyeball what that angle is, could you take a stab at what approximately the angle would be in degrees? Sure, yeah. Anything more than 270, though, right? Right. 275 degrees would work, because like right down here is 270, you know what I mean? There's another way you could do it, though. You could go backwards around the circle and call it negative 85 degrees. That's also valid. Yesterday I was particularly feeling athletic, and I tried to do like a full circle in a loop, if you remember that. I mean, if you wanted to, you could go all the way around the circle once and then go a little bit further. You know what I mean? And so you could call it 275 plus 360, whatever that is. That angle would also work. So we started with just some generic review on how angles work. And hopefully that wasn't too bad, because then we transferred into a new section where we talked about how there's a new way of measuring angles. And maybe it's actually not new. I actually think, from what I've learned, radians predates degrees. I like to think of a radian as like just that perfect slice of pie. It's about 57 degrees, but its rationale was if this side is like, say, 10 centimeters, and this side is 10 centimeters, if like the around the edge is also 10 centimeters, that's defined as 1 radian. Who calls me this room? Hello? This is Chris. Are you looking for Jan Orr? Oh, I have no idea where she is. Sorry.
Hello.
Susan Stack, can you please call 100? Susan, please call 100.
Wait, let me find a diagram from the other day there. It would have been, let's see, right about here. This one. This was defined as a radian, where whatever this side and this side are, if those sides are the same as the around the edge, that's defined as a radian. I mean, to me, it's like the perfect slice of pizza, right? Like if you were to cut that size of pie out of the pie, it's not too greedy. It's not too stingy, right? Like that's a reasonable slice, you know what I mean? If you were to be given, like, say, that little slice right here,
Oh, that takes you off.
oh, that's a little stingy, right? And if someone were to like try to slice out like this piece right here, they're eating like a third of the pizza. That's a little much, right? So I can see why radians actually would have been like one of the first ways of measuring angles, but there's a lot of downsides to them. For one, it's very hard to estimate radians because your brains aren't cued to that. You know what I mean? If I were to ask you to try to figure out how far this angle from here to there is in degrees, I think I could do it pretty easily. Like I'd say, well, that's 90, that's 180, so I'd guess that that's maybe like 150. It's pretty easy to guess that in degrees, right? But if I asked you how many radians it is, I might go, okay, well, I can fit like one piece of pizza around there and maybe like a second piece of pizza around there. So like maybe 2.5 radians. But like I don't really feel all that comfortable that like I've really done a good job of that. Does that make sense?
I take that one.
Yeah. So although radians, hopefully you'd agree, like sure there's some use. You're never going to use this again after this course. Like it's not going to happen, right? But I do need you to be comfortable being able to convert between them. So we spent a lot of time yesterday working on converting degrees to radians, where the rationale is that there are 2 pi radians in a circle, and that's the same as 360 degrees. So why don't we just try, let's just make up one more example, and then I won't be able to wait any longer here. So, shoot, where's the little drag thingy? How do I extend the page? There, it's over here. Okay, so let's say that I gave you 3.7 radians. you guys remember how to convert that into degrees?
You divide by 360 and
Close. It's
Well,
actually you
divide
put the
by 2
three
pi.
you put the 360 on top, and you put 2 pi radians on the bottom because radians then would cancel.
I did. Oh yeah.
And then like put 2 pi in brackets. So make sure you're really careful on that. So it would look like 3.7 times by 360 divided by bracket 2 pi.
Where's pi?
Found it?
I got something
Blue,
different.
Right beside the 8.
No, I know. Oh, I did 2.7. Just kidding.
No, 3.7.
Yeah.
Okay. So it looks like 3 perfect slices of pizza and 0.7. So like that would be a second perfect slice. That'd be a third perfect slice. There's like 3.7. Is that about 211 degrees, 212 degrees? Yeah, I guess that fits, right? So that's one skill I need you to have, being able to convert between the two. If I did the other opposite way and I said that you had 12 degrees, right? Then 12 degrees, you would say 2 pi goes on top and 360 goes on the bottom, because then the little degree symbol would cancel.
Wait, Shelby, I kind of fell behind there for a second.
Okay.
So I got the same thing as you did helping me calculate, but how do you get 12 degrees from?
Oh, I just made up a new number.
Oh.
So imagine a new example. If I gave you 3.7 radians, just as what I started with, say hypothetically a brand new example, let's say I gave you 12 degrees, what would 12 degrees be in radians? So then you'd take 12 degrees times by 2 pi, divide by 360, be 0.2 of a radian. I think that kind of makes sense though, right? Because here's like that perfect slice of pizza, which is about 57 degrees or so. And if you had to only use about 12 degrees is like that really chintzy little slice, right? And so, yeah, it's not a full radian. It's like 20% of a radian. So hopefully you'd agree. Radians, it could totally be a useful measurement, but not very purposeful like nowadays for us. Like especially teaching kids in high school, it's not that useful. I promise you though, if you were to go on in like trigonometry and angles, you almost exclusively work in radians because you might be able to see how like there'd be some value to being able to measure things in that sort of unit. So, all right, let's move on then.
I only have 2.
+1 for you?
Yeah, +1.
Okay, then we're good. Okay, so yesterday was basically my intro lesson talking about like, you know, what do we need to do in order to talk about sinusoidal functions. Today, now we're going to really dig into what do these graphs look like. So yesterday I showed you real quick what a sine graph looked like. And it essentially looks like this. It has this kind of like wavy up and down kind of motion to it. And there were 3 new properties we had to learn about. They were called the amplitude, the midline, and the period of a graph. Anybody remember what an amplitude refers to?
How high or how deep?
Yeah, that's pretty much the best way of putting it. How high, how deep the graph happens to be. That's an amplitude. So if this is a wave that you're riding at, like say, like you're a surfer, the taller the wave, the taller the amplitude. The midline is essentially like, what does it go like right to the middle of? Sometimes we find the midline first because it's kind of helpful to find where it goes right to the middle of. The period refers to like, how long does it take between cycles? So like, here's the high point right here. Here's the high point right here. The period refers to like, how far is it from there to there? Or how far is it from here to here? Does that make sense? Like a period is, well, yeah, how long between cycles? So let's start by doing some examples, I hope. Here's an example. This is a Ferris wheel. A Ferris wheel would actually fit sinusoidal data. Imagine that this is you. You would start on the ground, and then you would get to the very top of the Ferris wheel, and then you'd come back down. And then you'd ride to the top of the Ferris wheel again, and then you'd come back down. Does that make sense? Right? Like as you go around the circle, you start at the bottom, you go to the very top. Well, that's what's happening right here. And then from the top, you come back down again. That's you going back down. How many times did you go around the circle then on this graph? Twice, right? This little bit right here is from the bottom to the top, back to the bottom again. And then from here, bottom, top, bottom again. Right? So let me ask you then, let's try to find these 3 characteristics. Let's find the amplitude. Let's try to find the midline. And let's try to find the period. I usually recommend let's find the midline first.
80.
How'd you figure that out?
Because it looks like it's in the middle.
Yeah, I mean, essentially it looks like it's right through the middle at 80. 9 times out of 10, that's probably good enough. But let me give you some rationales to figure out how to find the midline otherwise. What's the lowest number this thing goes to?
0.
Actually, it looks like it goes as low as 2.
Oh.
Does that make sense? See how the point right there is
yeah,
at 2? So your lowest is at 2. Where's your highest?
160.
Looks like it's at 160. What is the halfway point between 2 and 160? It's actually not 80. The way you'd figure this out is you would add them together and divide by 2.
Might be 81.
It's actually at 81. You were really close. And like I said, 9 times out of 10, you probably just look at the graph and tell where it is. But the best way of figuring it out is find the high point, add the low point, and divide by 2. That's the easiest way to find where your midline is. So it's actually at 81.
Not bad.
You know what? It was a great thought, though, right? Like, you were super duper close. Okay. Well, based on that, we now need to figure out how high the graph goes. How far is it from 81 up to 160? Okay, let's say it was 80. How far is it from 80 to 160? 80, right? So if it's from 81 to 160, I believe it's going up 79. Let me double check all the way back down again, though. Oh, no. 81 to 160?
70. What? Yeah, 81 to 160, 79.
Yeah. How far is it from 81 down to 2? From 81 down to 2, isn't that also 79? So it shouldn't matter whether you're going up to the top of the peak or down to the low of the valley. Either one should be kind of the same. So your amplitude is a wave of 79 high and a midline of 81. Make sense? How about the period? How long does it take for this Ferris wheel to go all the way around the cycle once?
30.
You're right. That one is correct. Here's how I might figure that out. Here it was at the bottom at 0, and then it's back at the bottom at 30. And it's back at the bottom again at 60. It looks like every 30 minutes it goes around. Right. Or here's another way of looking at it. At the very top, it's at 15. When does it get back to the top again? 45. How far is it from 15 to 45? 30, yeah. So like there to there is 30, or here to here is 30, or here to here is 30. So your period is 30. Minutes, I guess, would be the units. Did that make sense? So one of the things you're probably going to be asked to do is take a graph and just look at the graph and tell me, like, what are some of these characteristics? Let's just look at this graph right here in general, the one that I've got plotted. Do you guys think we could calculate all of these characteristics just by looking at it? So let's start with domain. What's the domain of this particular graph right here? Yeah, sine graphs are back to being x is the element of the reals. Like, you can type in any number you want. Can you type in the sine of 5 or 6 or 7? Sure. Sine of 1,000,000? Sure. That just means that you went around the circle a whole bunch of times, right? If it was sine of 360, it just means you went around a circle once. Sine of 270 means that you went most of the way around the circle. Sine of 180 means you went halfway around the circle. But I mean, every single number is valid for domain. Range is different, though. Are there numbers way at the top and way at the bottom? Remember how I probably beat into your heads a lot the idea that there is no answer, sometimes there's an answer? If I were to ask you, when does this Ferris wheel get 100 feet off the ground? The answer is, it doesn't get 100 feet off the ground. That's above its range, right? This thing looks like it gets as high as...
I forgot my one is 12, I think.
What was that?
You go like block by block and it gets 12.
I think, yeah, right? This is 0, 1, 2, 3, 4. So that's 4. 5, 6, 7, 8, 9, 10, 11, 12. Yeah, good call. So then the way we'd phrase this is that it's as low as 4.
Negative 4?
As high as 12. I think that's positive 4. Because I think right here is like 0, 0 in this corner right here. Like we're only doing the positive quadrant of the graph here. And you would say that y is between 4 and 12 using that notation. Has to be bigger than the 4, but less than the 12. Are you allowed to have the little bar on the bottom of it? Does it actually get as high as 12? Yes. Yeah. Keep in mind, though, when you do some of the exponential and logarithmic functions, sometimes you have to write it as like y is just less than 4. You don't actually get the bar, but not in this example. The good news is that sometimes a lot of this thing is a repeat. Well, your maximum value is at 12, right? Your minimum value is at 4, right? That still hasn't, we just found that. What about a y-intercept? Does it have a y-intercept?
No. Yeah.
Actually, that would be right
Oh,
here.
So 0?
Well, it would be at 0, comma something.
0?
Well, let's count it.
8.
0, 1, 2, 3, 4, 5, 6, 7, 8. Right, now, this particular function, does it have x-intercepts?
No, it doesn't.
Actually, no, it doesn't, because the x-intercepts would be down here. Imagine this was a Ferris wheel. The x-intercepts of a Ferris wheel would be where the Ferris wheel hits the ground. That'd be a bad Ferris wheel if you kept crashing into the ground over and over again. So sometimes it's actually very important to lift the function up a little bit so that it doesn't have x-intercepts, but you're a little ahead of me. Yesterday I showed you some graphs where it's very possible to have a graph that looks like this, where if I asked you to find me the x-intercepts, you would never be able to stop because there's one here, and here, and here, and here, and here, and there, and it would just keep doing this for forever, right? So often if I ask you for x-intercepts, we might only do like the first 1 or 2 of them, but this particular graph does not have any, actually. Yeah, not applicable. Okay, well, let's find that midline now. So these are the new properties that we're learning about, midline.
That'd be 8.
I think it's 8, yeah, but let's prove it to you another way. The lowest number you have is 4. The biggest number you have is 12. That adds to give 16. If you cut that in half, it's at 8, which visually looks like that's what it should be, right? Then for the amplitude, well, how high is it from 8 up to 12? I would say, well, 12 minus 8 means it's 4. Or how far is it from 8 down to 4? 4. Either way, the amplitude is 4, right? Like it goes up 4, down 4, up 4, down 4. Last little bit is to find that period. So we need to figure out how far it is from, like, say, here to here.
8.
Okay, cool. It was also 8. Or, by the way, you could go from, like, say, here to here. 1, 2, 3, 4, 5, 6, 7, 8. So, that makes sense? Awesome. Okay, let's try another one. Domain. Yeah, even though this graph only shows that it goes from 0 up until about 720, this graph does keep going for forever, right? Why don't we do max and min before we do the other ones? Visually, it looks like the max value is at about 7, I think. A negative 3. So let me write that out here. Your max value is up here at 7. This one's down at negative 3. So to write my range, I would say negative 3 is less than or equal to y, which is less than or equal to 7. I'd like to point something out here. What is different on the x-axis between this graph and the one back here? I was actually going to point out that it puts in degrees. I haven't talked about that yet today, but you have to be very fluent and comfortable on your graphing calculator in converting between radians and degrees.
Please excuse the interruption. Mr. Orr's 7B class, so 7B for block 6. You are going to Mr. Schultz's classroom, which is 213. So Mr. Orr's 7B, block 6. You're going to Mr. Schultz's classroom, 213. Tatum Brown, can you please come to the office for a phone call?
All right. Where was I? Let's just keep going. Y-intercept looks like it's down here at negative 3, right? Okay, so for this one here, this is a bit more challenging. If we wanted to find the x-intercepts, you'd be doing this for forever, right? Like, so usually what I might ask you to do is just tell me how many x-intercepts there are. I've seen that question before. So I would ask you on the graph between 0 and 720, how many x-intercepts are there? And I might say that there are 1, 2, 3, 4, 5, 6, 7, 8 x-intercepts between 0 and 720. There is a 9th one, but it's after 720. Does that make sense? I might ask you where the very first one happens to be. If I had to guess this thing, that would be what? 120, 60 is probably right there. So that's probably at like 30, probably. But I just want to point out, like, there'd be a million of them sitting there, so you'd never calculate them all. Okay, let's try to find that midline. Anyone figured it out yet?
2.
Yeah, I think so. Because what you need to do otherwise is take 7 and minus 3, add them together, which would be 4. Cut it in half, 2. Sometimes we write the equation y equals 2. Sometimes we write it as an equation, or you can just tell me that it's 2. How tall is the graph? How far is it from 2 up to 7?
5.
Perfect.
What did
And-
you write for x-intercepts right there?
Oh, I wrote 30 degrees, comma 0.
Okay.
I wrote it with a degrees sign right here. I'm guessing this one right here is probably like 150 degrees, maybe. I don't know that I can tell exactly where it is just by looking at the graph. But you guys know how to use an equation and find them on your calculator, right? The point I want to make, though, is it's the etc. that's really important. There's a million of them. Like, it is literally infinity is how many intercepts there are. So you would never search for all of them. You might search for like a couple. Oh yeah, last little bit, we got to find the period.
It's 3.
Yeah, it looks like from here to there is like 1, 2, 3 boxes. But I don't know that that really works, though, because we got to figure out how big each box happens to be. So like 1, 2, 3 boxes takes me to there. Let's see, 1 to there, that's 60 degrees. There to there is 120 degrees. There to there is 180 degrees. Does that make sense? So if each box is 60 degrees and it's 3 boxes worth, I believe the period is 180 degrees. Every 180 degrees it repeats itself. Does that make sense? So from here to here would be 60 degrees. Here to here would be 120 degrees. Here to here would be 180 degrees. Still good? Those kids are loud. Okay, why don't you try this one without my help then? So here's a picture of a graph. Find me all these properties. See if you can do it without me. No, it just said it on the announcements.
So you find the midline by adding.
Take like the top and bottom numbers, add them together, and then cut it in half. And that should find you a midline.
So like,
Should we take bets on how many kids walk into the classroom without listening? I got 3.
I got 3.
3 kids are going to walk in the classroom without paying attention. You guys think it's over 3 or under 3?
I think it's like gonna be like 2.
I think 3 is a big number.
3 is a good number? We'll see. That's already 1, so.
Are we counting like tomorrow as well?
No, let's just count just today. We can take bets again tomorrow.
I would say 2.
You got 2?
Let's do a probability problem, guys.
Yeah, probability.
How many in there on that grade?
What is the probability that a grade 7 kid doesn't listen?
Very high.
What's the probability that a grade 7 kid does listen? Okay, let me throw a few of these down here. Domain should be x element to the reals.
How do you find the amplitude? That's what I forget.
Okay, let me get to that one in a second. The max value is 2 and the min value is minus 4. I think everyone should probably be able to see those ones. So it means your range is going -4 to y to 2. That one so far so good?
Yeah.
The y-intercept, I just need to look. It's just sitting right there at -1. So that's 0 and -1. How many x-intercepts are there total?
2.
Well, visibly 2. But like, there are a billion. There's infinity of them. But like, we can just label a couple of them. So it looks like that one's right there at probably 0.25.
Yeah.
And that one's going to be at 2.25. But like, I'm going to write the word etc. there because there are a lot of them. So one question you might get asked then is between 0 and 5, how many x-intercepts are there? And you'd say there are 2 x-intercepts between 0 and 5. But if I made it from like say 0 to 72, there might be more x-intercepts. So, okay, let's do the next ones. Midline. To find midline, we need to figure out where the halfway point of the graph is. And I'm pretty sure it's at -1. The way you can figure that out is take 2 and -4, add them together. Gives you -2. Cut that in half.
2.
2.
Oh,
Only-
okay.
Ooh, no, we got to count how many times the door gets opened. Okay, so I got one more.
I got no more. Hopefully no one else comes.
Lisa, are you on 2?
Yeah,
You picked 2?
I picked 2.
Anybody pick more than 2? 4.
1.
Okay.
That's a teacher. It doesn't count.
Does it count?
Oh, they definitely count.
That's a
But
teacher.
we said students at the start, so it's just.
Everybody good at the midline though? Okay, so to figure out amplitude, I don't really have a fancy formula for amplitude. You just got to kind of count, like how far is it from -1 up to 2? Like how tall is it? Well, from 2 down to 0 is 2, right? And then down to -1 is 1 more. So like your amplitude is 3. Does that make sense? Or from -1 down to -4, how far is it from -4 to -1? It's 3. By the way, we always make the amplitude a positive number. Even though the amplitude goes up and down, we always define it as a positive number regardless. How'd you guys do on those first ones?
Good.
Anybody get the period?
No.
The period's really challenging on this one. You got it. How'd you figure that out? You are
kind
right.
of messed around with it. What I did is I went to the halfway point of that first wave,
Yeah,
and I realized it was 1.25, and then I times it by 4.
that'll work. Okay, so you like went from right here, figured that was 1.25.
Yeah.
That's clever. Because really, if it goes up in 1.25, it's going to have to come back down in 1.25. What I did myself is I figured that the halfway point was 2.5.
Yeah.
Well, I figured that the other half of the graph, it has to go all the way back down and back up again. So if from here to here is 2.5, wouldn't from here to here be also 2.5?
Yeah.
So if I add it together, their period is 5. But I mean, your logic is just as sound, right?
Well, I tried
Each
I
quarter
tried
is
yours
the same.
To double check.
Yeah, really good job there. So the reason why I wanted to show that one here is they may not give you enough graph to fully see like when the next time that it gets way up tall up here is. So you may have to use some different logic and realize that you can separate it up into quarters. You know what I mean? Like this is the first quarter, this is the second quarter, this is the third quarter, and then back to there would have been the fourth quarter. Like you can do that. You can even separate it into halves. Here's the half that's above ground. Here's the half that's below ground. Did that logic make sense though? Cool. Good for you, Shody. That was awesome. Okay, well, now let's move on from me giving you a picture though to let's start talking about if I give you an equation like this, because this is probably more typical. I'll give you an equation, and we want to try to calculate those same sort of characteristics. So the first thing I want to recommend we do though is we should all be in the same either radians or degrees. So we got to pick one to go with. It does not matter at this point which one we pick, but we should make sure we're consistent.
Degrees.
Okay, let's go with the degrees first then.
Wait, hold up. How do I do that?
Okay, so good question. So if you're on just like a regular old home screen, press mode, which is the button right next to the second button,
Alright.
and then toggle down between radians and degrees. So if we're saying degrees, that's fine, but we got to know that that's what we're doing.
Alright.
So degrees we're going with. And let's type in 3 sine x. Now, one more thing though. If I just press graph without looking at it too much, I may get a good picture. Or I may get something completely useless. Like this isn't bad. But if you were to do like a zoom standard, it looks like this perhaps, which is useless to you. So we need to make sure we understand the context of our window. How in degrees, how long does it take to go all the way around a circle? 360. And we're currently going from -10 to 10. So you might want to go from like say -10 to, I'm going to do this. I'm going to go 720. Why would I pick 720? What's that? It's going around the circle twice. It's twice 360, right? And then negative 10 to 10, I think I can go with that. So try doing what I have here. Negative 10 to 720. And then negative 10 to positive 10.
That's a good graph.
And it looks very similar to what I've given you here to work with. And you can kind of see that the graph does like this and there. And then it does it a second time. And obviously I'm not drawing it very nicely, but this wave would repeat itself forever, right? Okay, let's try to find some characteristics. What is the domain? Well, anything you'd like it to be. Okay, this one's a bit trickier. We need to be able to find the range. We need to figure out how high and low this graph gets. Now, I'm only going to do this method here once, and then after that we're going to use our common sense, but you could try to find the minimum value. And it doesn't really matter which minimum you pick. You could just try to calculate how low does this thing get. It goes as low as negative 3. Anyone want to hazard a guess as to what the maximum value is going to be? Probably positive 3. I mean, let's just prove it this way using a maximum. But after a little while, you'll actually be able to just tell what the maximum minimums are just by looking at the equation of the graph. There, it gets as high as 3. Look at the equation I wrote out. Y equals 3 sine x. Y equals 3 sine x. Huh.
Golly, I wonder what's going on
Wow, I wonder where that came from, right? The number that goes in front of the equation, that leading coefficient, what it does is it makes the graph have more amplitude, essentially. If you want a graph to have more amplitude, throw a number in front. That's what it'll do. So now we should be able to write our range. It's going to go as low as negative 3, as high as 3, and y is in the middle. Okay, y-intercept. It looks like it's going right through 0, but just as a quick confirm, find the value when x is 0. Yeah, it's 0. Okay, for your x-intercepts.
0, 0.
Well, for sure that's one of them. Yeah, this one's at 180. After a while, you kind of figure out the pattern.
So would the next one be 360?
Yeah, like once you figure out a pattern, you can go with that. But if it's okay with you guys, I'm just going to say etc. Because to find x-intercepts, I can't give you a hard and fast rule. It depends on how they ask the question. If they ask you find all the x-intercepts in the picture shown, then find them all, right? If it asks you how many x-intercepts there are, then find those. But at the end of the day, you need to know that there could be an infinite number of them. And like we'd never find them all. So the midline.
Isn't it 0?
Yeah, it should go right through 0, doesn't it? Yeah. I actually have a reason for that, and I'm going to show you it right now, actually. You know how there's a leading coefficient to certain graphs? There's another thing that we do to graphs where if we have like a constant term at the end, remember how a constant term at the end kind of can affect things? Well, there is a constant term here. It's plus 0. And because if there's a plus 0 at the end, it means that the midline is actually right through the middle at 0. Watch, don't change yours, but watch what happens if I do this. Sine x plus 8. The midline is now way up here at 8.
Whoa.
But then your amplitude, or your like height and everything stays.
Your amplitude is still going up and down by 3s, but now the graph is just higher up, that's all. So the number that goes right in front actually affects your amplitude. And if there's a constant term afterwards, it actually affects your midline. And we'll see that more in future examples, but that's why it's right at 0, is because there's a plus 0 on our graph here. Oh, shoot. Try that again. So amplitude. How high is the graph getting to?
3.
Yeah, I mean, literally the amplitude is straight up this number right here. I'll give you that as an always, by the way. Like whatever this number is right here, that is your amplitude. The hardest part is probably finding the period, trying to figure out how long it takes to repeat itself. But that actually can be done with a little bit of common sense as well. We're in degrees, right? How many degrees are there in a circle? Well, that's how long it takes to repeat itself. From here to here is 360 degrees. And then from here to here is where it made it 720. What was that?
It's 180. Oh no.
No, because I went from 0 to 720.
Yeah. The instructions. Darcy and Kimberly Walker, please come to the office for checkup.
So
Darcy and Kimberly Walker, please come to the office for checkup.
in a
The
normal
baseball practice for tonight has been canceled, so no baseball for tonight.
in a normal graph, the reason why it's 360 is because that's how long it takes for you to get all the way around the circle. Think of the Ferris wheel example. Here you're starting at the bottom of the Ferris wheel. Here you're going to the top. Then you're back at the ground level. Then you're below, and then you're back again. Well, that's going to take you 360 degrees because that's all the way around the circle. Here's you going up. Here's you coming back down. Here's you going below bottom part. Here's you coming back up again. Do you guys see the correlation here? Here's the up.
Yeah.
That's this bit. Here's the back down. That's this bit. Here's the below ground section of it, like that. And then here's you coming back up to the start line again. See how like this graph kind of fits with a circle? Okay, let's try another one. Let's not graph it though. Not on our graphing calculators. Let's just talk about what the one thing is that's changed.
There's no leading.
There's a +2 and there's no leading number. Well, actually, no, that's not true. There is a leading number. It's number 1.
1.
Yeah. So without even graphing it, I should be able to tell you what this is going to look like. There's going to be a midline going right through the middle here at 2. And this thing is going to go up and down by 1. So it should go up 1, down 1, up 1, down 1. It should be a very like thin sort of wave. Does that make sense? Like this is not a tsunami kind of ride the waves surfing kind of thing. This is like it's a little bitty wave. Does that make sense? And I mean, now that I've done this by just knowing its properties, knowing the middle should be at 2, and then it goes up 1 and down 1 and up 1 and down 1.
So that'd be 1.
Let's graph this thing now and see whether that actually goes through. What did you say, 1 and 3? Let's test it. So clear this off. Sine of x. By the way, close the bracket. And then at the very end, add 2. Make sure you close off that bracket. It makes a difference.
Mine's at 720 still. Is that bad?
Yeah, mine's still going to 720 as well, right?
Okay.
That's why I drew this thing in here twice. Because it's going to go up and down once, up and down twice, because 720 is going around a circle twice.
Yeah.
What if I were to make it go to 360? Well, then I should see this thing go up and down just once, because 360 is a circle.
So amplitude is 1.
Yeah. So let's talk this through. Domain, anything you want. Range, I think, Cole, you said it a second ago, it's going between 1 and 3, right? Because the max is 3, the min is 1. Where's that y-intercept at here?
It's at 2.
Should be 2.
Yeah, I think it's right there at 2, which is like this last number. Hang on a sec. Isn't that a rule we had way back when? Is the constant term is the y-intercept? We can use that again now. X-intercepts? Actually, we don't have any. Which, in a lot of word problems, is actually a good thing. Because if this is a trampoline, and this is a person bouncing up and down on a trampoline, we don't want them to hit the ground because that's bad. Right? So, yeah, bottom out. So you guys have the rest. The midline is 2, the amplitude is 1. The period, then, is back to being 360 degrees. And I can tell that because, well, that's what it takes to go around a circle. 360 degrees. What if we were in radians?
357. Oh, it would be like 6.
It would be 2 pi.
2 pi. Oh.
Right? Because 2 pi is what 360 degrees happens to be. The radian unit of measure is a little more confusing. So let me show you how this might change then. If I were to go to my mode and change it to radians, then the graph looks kind of nuts. The reason why is that my window is letting me go up to 360 radians. It might be better to have it go to 2 pi worth of radians, because then that's just like one iteration around the circle, right? Like from here to here is just doing it once, as opposed to doing it like 360 times. Everybody cool on that one? Okay, let's do a twist here. This one will graph. So try to graph the sine of 2x. And make sure that we're all back on the same conditions. So make sure you're still in degrees. And make sure your window is going from 0 to 720.
From 0 to 720?
Sorry, from -10 to 720, I guess. That's what I had. What happened here? Okay, well, what's the midline?
0.
Why is it a 0?
Because there's no.
There's a plus 0 there, yeah. Right? Doesn't this look like it goes right through the middle here? What's the amplitude? Yeah, it's 1, because there's a 1 written in front. But you know what's changed about this one here? Is normally I would expect the graph to go up and down twice, right? Because we went from 0 to 720. 720 is going around a circle twice, but it didn't go around the circle twice. It went around the circle 4 times.
So 80 times 360 times 4.
Well, it's this 2 right here. Okay. Let me change my window real quick here. Let's say I went from 0 to 360. Normally, from 0 to 360, I'd expect this to go up and down once. But it's going up down twice. And that's what this 2 does right here. If you put a 2 or a 3 or a 4 here, it makes the graph go up and down more frequently. Watch this. Currently, I'm sitting on a 2. Watch what happens when I make this number a 3. Now it goes up and down 1, 2, 3 times. Watch what happens when I make this number a 5. I'm sure you can guess. The graph's going to go up and down 1, 2, 3, 4, 5. Does that make sense? This number right here, what it does is it changes the frequency of the graph. Okay. Does that make sense? If you put a 2 there, it happens twice as often. You put a 3 there, it happens 3 times as often. You put 100 there, it happens 100 times as often. Does that make sense?
So it just kind of doubles it in a way?
Yeah, well, because of the 2, it doubles it. But here's how that works for us, though. Although the frequency happens more often, what it does is it shortens the period. The amount of time between these things is actually less. It used to be, let me just graph an original one here. Here's the sign of just like good old-fashioned normal x. See how this one's just going to go up and down once? How long does it take for it to go up and down once? 360, which is, by the way, what my window is set to, right? Well, what happens if I put a 2x there? If it normally takes 360 to happen, but now it happens twice as often.
Wouldn't it be like twice? Why'd you divide it?
You would divide it. It's 180. Because what's happened now is if this is 0 and this is 360, like my current graph is showing, from here to... No, that's not right. From here to here is now 180. It actually, because it happens twice as often, the period is actually shrinking. Does that make sense? So the key to this one right here is if you want to find the period, you take this number right here and you divide it. Well, you actually divide 360 by that number. So if this number here is 2, cut it in half. If this number is 3, cut it in third. If this number is 5, cut it in 5. Does that make sense? So there's actually a formula on your formula sheet that's very similar to that. Do any of you guys have formula sheets nearby? Formula sheet. If you have your formula sheets nearby, they actually put a formula on here. They call it this. Period is equal to 2 pi divided by b. Now, I've been working with you guys in degrees. We're going to have to do some more radians in a bit here, but you know how 2 pi is the same thing as 360? Basically take 360 or 2 pi, and whatever that number is that's inside the little brackets there, divide by that number, that's what your period happens to be. Because this basically makes it happen more often. So if it happens more often, the length of time between them is shorter. Let's move on. Let's try this example then. Let's put all of them together. We have a number in front, we have a number in the back, and we have a number right here. Let's talk before we graph it about what should happen, and then let's graph it to confirm. So what should this 2 right here do to the graph?
The amplitude.
Amplitude's 2. It should be going up 2, down 2, up 2, down 2. What does the 3 at the end do? Midline's now at 3. So I'm actually going to start with that. I'm going to draw a midline right here at 3.
And your y-intercept.
And it's going to include my y-intercept. Yep. It looks like it goes up 2, right? So it should go up 2 and down 2. And maybe up 2 and down 2 and back up again. And I guess it kind of depends on what my window's set to, but that's what my graph should kind of look like. Except what does that 5 do?
It's 360.
Yeah, it means that your period is now 360 divided by 5.
72.
So every 72 degrees, you repeat this thing. So let me make my window size. Whoa. Why don't we change the window size compared to what we used to be doing? Why don't we say that this is from 0 to 360? Normally, how many times will this go up and down between 0 and 360? I'd say once. But with that 5 happening right there, it's going to have to happen 5 times. So I'll put my midline back here at 3, and I'm going to go up and down 1, 2, 3, 4, 5. Not my greatest graph, but does that make sense? Okay, we got to make sure all our window sizes and stuff are the same. So let me graph this thing now. Y equals 2 sine of 5x, close the bracket, then add 3. And then for our window size, let's go from negative 10, just to give it a little bit of leeway room over here, to 360. And negative 10 to 10.
Got it.
So that'll be negative 10, that'll be positive 10, that'll be negative 10 and 360. And hopefully I'll watch this thing go up and down 1, 2, 3, 4, 5 times. The distance between these peaks then, what did you guys say it was? 72 degrees? There you go.
If you set your graph at instead of 360 just to 72, then it only shows it once.
Then it only shows it once, right? Like if you're saying if you go up to 72, shoot, screwed that up. If you make this go to 72 is what you're saying, right? Yeah.
And then it just shows it once.
Then you'll just watch it happening once, right? Yeah. So the trick to these ones here is that you really have to know what your window size happens to be, right? Because if you accidentally set your window size to go to 2 pi, well, that changes everything, right? Because like 2 pi only goes up to 10. Or sorry, 2 pi is 6.28, right? Well, 6.28, like that's hardly even started, right? Because it takes at least 72 degrees to go up and down again. So you really got to make sure you watch your window sizes. Does that make sense? Okay, let's try some word problems then. Actually, you know what? Why don't we take a 5-minute break real quick here? Because I've been talking for a while. You guys have been doing well. Take 5 and then we'll come. Wait, why don't we keep going here? Okay, last set of notes. I know you probably don't have these in front of you, but I pointed out all the outcomes that I'm supposed to teach you. So here are those outcomes one more time. You need to know, for this section here, how to represent data using sign functions to solve problems. Long story short, they're going to give you a word problem. Okay. Don't stress over it, though. It's very similar to every other problem-solving thing you have. They're either going to give you some data, and you have to do a regression using L1, L2, Y1 sort of thing, or they'll give you an equation, and you do things like solve for the x-intercepts, the y-intercepts. You have to do that sort of thing. So let me show you a couple of word problems then. So, try not to stress, but, I mean, plan on getting a word problem. So here's the first one. The number of hours of daylight in a caloid is represented by this function. First thing I want to point out is there's one extra thing to this function you didn't have last time. There is a number right here. Okay. This is your amplitude. This will help you find your period. And this number right here is your midline. They'll also possibly have a number sitting right here. It does not actually have some sort of meaning in terms of one of those things. What it does do, though, is it kind of shifts the graph side to side a little bit. So you know how I told you that this constant term could be your y-intercept? That may not be true, actually, if there's a number right here. Okay. So when I first showed you graphs, I didn't put a number here, but this one, it's going to tweak it slightly. So let's graph this thing. So type in y equals. That one's me. So let's type this in, 8.245 sine. Okay, I need to point out how this works here. Do you see how when you type in sine, it opens a bracket for you automatically? Mm-hmm. But right here, it didn't open a new bracket till later. What that means then is you have to put a bracket here, then type in like 0.0172, then open another bracket for x minus 80.8988.
980.
Close a bracket, but then you actually have to close a second bracket. It kind of implies that there's a bracket around all of that stuff. And then you get to add the 12.585. So before you press graph or anything, Double check and make sure that yours is exactly typed in like mine is.
So we do 2 brackets after the. Yeah.
I'm confused.
Okay.
And then we just graph it.
Yeah. So the thing here is like, see how there's no bracket written right here on the sign, Shody?
So it didn't work.
Yeah, it's not going to work because I got a couple of reasons for that. The first one is, you know how we've been working with degrees the whole time? Yeah, this is in radians. Do you see a degree symbol on any of these things right here? I'd say no. So chances are, 9 times out of 10, I'm willing to wager, they're actually going to put these in radians. So we have to go change our mode to radians.
How do you do that?
So press second, like just go mode, I guess. Mode. And then it's right next to the second button.
You're changing it to radians?
We have to. Do you see how none of these things have a little degree symbol afterwards?
Yes.
If there's no degree symbol afterwards, it's implied that it's probably in radians.
So then we have to change the window.
Okay, and that's the other thing. We got to change the window. Now, the context of this function is we have a graph where x is the day number in the year. Well, you can't have a negative day number. And I think we probably know how many days are in a year. 365.
I thought we were doing the whole like 2050.
We'll do that in a second. For y minimum and maximum, the y value is how many hours of daylight you get. Can you have negative? No, okay, you can't have negative hours of daylight. What's the most amount of daylight you possibly could have in a day?
12 hours.
I'd probably say 24.
Is it 24?
Of sunlight. Well, I'd say 24 because you guys ever seen like up north, sometimes they have the sun out like literally all day long. You ever seen that before? Like land of the midnight sun?
No,
So-
I can't say I have some.
Okay, well, I'll have to show you a picture in a little while. Like literally the sun never sets when you get really far up north sometimes, or there never is any sun. Like it's either perma-darkness or perma-light. So now if I graph this thing, hopefully it looks kind of like what I'm hoping for, where you've got a nice little sun curve.
It still won't work.
Mine's like straight across.
I'm radian. So it's on radian.
Okay, we're on
Isn't that what we just typed in?
Why?
Okay, so we need a double bracket here. We need an extra bracket there.
Oh, so that's all you're on.
That's right.
Double bracket there.
Are you guys in degrees or radians?
Double bracket. Double bracket.
No, we're in radians. That's what I meant.
Ah.
Wait, what'd you say?
Oh, you need to go from 0 to 24.
Oh,
You would put it in the wrong spot there.
Yeah.
Okay, now yours is working. Yours is working. Anybody else need troubleshooting help?
I'm born. Class rules.
There we go. Okay. So
What does it mean by keeping things earthbound?
what needs to happen is
Alright, do you believe in God?
Keeping things earthbound meaning keep everything in the ground.
Don't throw anything.
okay. Anybody else have issues, or are we good to solve these 4 questions then? We're good. Okay, so let's try to problem solve now. We need to figure out how many hours of daylight would be on February 25th.
So once you count, like,
Okay, well, what day of the year is February 25th? Well, it's not the 25th day of the year, right? How many days are in January? 31 in January.
Oh, you guys
31 days in January, plus there's 25 more days in February. So we're looking for day number 56. Well, then just do this. Second, calculate the value on day 56.
well, mine didn't show up.
Wait, what did you
Second, calculate the value when x is 56.
Oh.
The value when x is 56.
9.15.
Yeah, let's call it 9.1. 9.1 hours. That makes sense.
Yeah.
Anyway, where's the longest day of the year? Yeah, your maximum. That's the longest day of the year, where there's basically the sun barely is setting that day.
July, I bet.
Probably is, right? Let's try to find that day.
Date. 172.
Day 172?
Yeah.
Which, that's got to be in what, July, give or take? June, probably?
172.3. So
Yeah.
just 172.
Yeah, let's just call it day 172. Should work. So those are the sorts of things where you can use your graphing calculator for. Part C, though, you can't use your graphing calculator nearly as easily because in order to find the period, we'd need to know like when the top meets the next top one. And I have a better idea. There's a formula for period. The formula is take 360 and divide by whatever that b value is. This number right here is b. Only we're not working in degrees, we're working in radians. So that formula off your sheet is take 2 pi and divide by 0.0172. 2 pi
365.
divided by 0.0172, shockingly, is 365. Which kind of makes sense because
Like 3.
that's how many days there are in a year, right? That kind of makes sense, doesn't it? So,
Oh.
How many days would there be 8.5 hours of sunlight? Well, all of them are gonna have 8.5 hours of sunlight.
no, because sometimes what they have is, like if you get really far up north, sometimes they have the sun all the time out, and sometimes like the sun is rarely out.
So
So
don't you have to do y?
that's what we need to do. We need to do where y is equal to 8.5 and figure out whereabouts there's 8.5. Because look, in January they might only get 7 or 6 or 5 or 4 hours of sunlight. And over here in November, December, January as well, they might have limited amounts as well. So how do I find these locations here?
Oh crap.
Intersect, yeah. To save time, can I find the first intersect, and can some of you guys find the second intersection point?
I found the second one.
Oh, well ahead of me. Okay. Give me 1 sec to find mine first, then.
Thanks, Keely. I'm gonna ignore the sarcasm there because you're irrelevant right now.
Ouch. Okay, so it looks like the first day, the first time it hit, it's 8.5 is about day 51.
And the other one's 293.
And day 293. Okay, so between those days, that's when there would be at least 8.5 hours of sunlight. So it looks like in January and February, they don't really have a whole lot of sunlight, like they have 7 or 6 hours of sunlight. Which, I mean, doesn't that make sense? Like you guys, we kind of have a similar thing here, right? Where, like in the middle of the wintertime, the sun doesn't rise until, what, like 8 in the morning? Maybe?
Or later.
And then it starts setting at like 4:30. You know what I mean?
Those
So
are the
like,
worst days.
those are the worst days, right? Well, the further up north you get, the more exaggerated it is. So sometimes you might only have like 5 hours of sunlight in the day. It would suck, wouldn't it? All right. Did that make sense? Can you guys handle that?
Yeah.
Okay, let's try another example.
So
They-
if it was like 293.7, you wouldn't.
You'd probably have to say that it occurred on day 273, probably.
Okay.
Yeah. Okay, here's the other thing they might ask you to do. Rather than give you an equation, I might give you some data, and hopefully you kind of figure out where this is going. You're going to have to type the data into your calculator, make your own equation. So I'd prefer, maybe let's save some time. Let's just talk about how you'd solve this, as opposed to actually solving the whole thing. We would press Stat, Edit, and we would type the data into here. Everybody okay with how that would work? But then we would go to y equals. We'd get rid of all the old stuff we don't want. We'd turn on a plot. And ideally what it would do is it would give us a graph where it would hopefully have like some points that kind of go up and down like this. Does that make sense? We would then need to calculate something. So we'd go Stat, over to Calculate, and this is the one we haven't done yet. It's all the way down in the letters. You got to do sign regression. And if you did a sign regression, you'd have to tell it like the L1, L2, Y1 kind of thing. And ideally, it should make yourself an equation. Well, at that point, the question is the exact same as what we had before. How would you find the amplitude? Yeah, it would give you an equation, right? The equation would be like y equals 17 sine of 0.173 bracket x minus 80 plus 2 kind of thing, right? Like it's going to give you an equation. Well, whatever this guy right here is, that's your amplitude. Does that make sense? To find your period, all you do is you take that number and take 2 pi and divide it. And that'll find you your period. I'm pretty confident it's going to be 365 though. because that's what a year is. Okay, this one would be challenging. To find the length on day 18, you'd have to figure out like July 18, how many days into the year it is. So, July 1st would be 182. So July 18, I think, is day 200. And then when's the shortest day of the year? Minimum. Find the minimum value. Does that make sense how you'd go about solving it? Okay, let's just skip to the last one, then we'll skip this one. We'll do this one next. So last one here. This is actually the same sort of thing where we have to put in our own data, but this one's a little bit shorter to do. So why don't I give you guys about a 5-minute head start. Can you guys get this data typed in, start getting an equation going, and then in 5 minutes I'll try to catch up with you. So try this one as the one we do instead.
Oh, crap. How do I, like, if I messed up, I have to start all over again?
You may have to.
I just need to
27. Okay, so then like go back up and then back down again and rewrite over top like that. Only I screwed that up, so you need 27.75. So like press enter, go back up and just rewrite over top of it. You do it.
Okay. And
Oh yeah, we forgot to keep track of how many kids came. Only 2, huh?
I win.
Shoot, I lost.
Keely, did you win too?
Nice.
I count that teacher.
No.
Teacher's the third person.
Yeah. He came in here.
You said students.
3 students.
Okay, we'll have to do the same thing tomorrow.
I'm saying it's 1 tomorrow.
1 tomorrow?
Yeah,
I'm gonna say it's 3 tomorrow.
I'm going with 1.
Oh no.
0. 9.25. 1850. 27.75. 37.00. 46.25. 55. 50. 64. 75. 74. 00. 49. 295. 541. 295. 49. This is a bit repetitive, isn't it? 295. 541. 295. 49. Okay. Yeah.
Me too.
I'm sorry, push function. It doesn't have that.
Because you're doing a one variable statistics. You're trying to do stats.
That is a huge number.
Sign regression. Because then it asks you for your L1, L2.
I was like, what?
And then this one needs to be like a L1.
Okay, there you go. I already got it.
You might need to turn your plot on though.
Hey,
It says plus -1
I lost.
on mine.
Interesting. Sometimes it's easier to try to get the information from right here. So like I'd say that's your amplitude. If we divide that from 2 pi, that's your period. This number means nothing to us. Your midline's 295. That makes sense? Like it might be easier just to get it from that information there.
Okay.
Hey, Chuck, do you have it?
Yeah, for sure.
I just forgot.
Okay, so what have we got so far? You've got data sitting in here. Okay, so let's turn the plot on. We will zoom 9 to try to get some of these points.
This is wrong data. This is
Oh,
like
you haven't done the data yet.
No.
Okay, sorry. Let's put in new data. Okay, so maybe you do this here then. So type in like 0, 9.25. Like, can you handle typing that stuff to get started? Okay. That's what we're doing in a
So
second.
wait, what numbers? So like A.
So like I'd read it like this. It's 246 times the sine of first bracket 0.17. Then open a new bracket for x minus 1.57. Double close the brackets and then add 295. That's kind of how this thing works. Only often we don't write that. There's some brackets right here. So this is your amplitude. This is your period. And this is your mid. That number right there doesn't mean.
Okay.
Has everyone got the data typed in so far? Okay. So minus Shody here. Just catch up with me when you got it typed in, okay? Go to y equals, turn on your plot. Okay. And then I would press zoom 9 for zoom stat. And hopefully you get data that as you look at it, it looks like it's going up and down, right? So then type stat. Go all the way down to sine regression and start doing a sine regression. Hello. This is Chris Rock. He's trading classes with me. Oh, I have no idea. Whatever my room is, 213. Okay. Okay, so type in the sine regression, and then depending on how your calculator works, mine I have to type in, oh goodness, I don't want it twice, L1, L2, and then tell it that I want the data to be in just one of the equation spots.
What's your window actually?
Well, that's the cool thing is if I do zoom 9 for zoom stat, it'll make a window for me that kind of like fits really nicely.
Yeah.
Yeah. So hopefully you have something similar to what I have here where the graph is just going up and down like that, right? Does that make sense to everybody else so far?
What was that? What was that last step to get the line?
You had to do the whole stat, calculate, scroll below delete, middle row, second one down.
What? Oh, wait.
Like, sorry, middle column, like, you found it?
Yeah.
Okay. And then scroll all the way down until you get to the sine regression.
Okay.
Okay. Then you got to do the L1, L2, Y1 thing. I'll just come do it.
So I went stat, calc, right?
Stat,
No.
calc.
Oh, okay.
This stat,
I
that
went
calc,
calc.
you want that calc, yeah. Sine regression. And then we just need to tell it where to put the equation. Remember doing this? Okay. And if you do like a nice zoom 9, should have what I have now. Everybody else okay with where we're at? Okay. No, I lost somebody. Okay. So hopefully you have a graph that looks something like this. Here's what I might recommend first though. Write down the equation. Go like second quit and get like all these numbers. So the ones that matter to you are A, B, and D. The C value has no relevance on our lives in dash 2. It does do something to the graph, but it's not relevant to us. So the equation is like 246 sine of 0.17x minus 157 plus 295. But the numbers we care about are the first one, the second one, and the last one. Those are the ones we care about. How do I find the max height of the Ferris wheel? Well, I could go to the graph, and I could just try to find out, well, how high does this thing get to?
It's 540.
Yeah, it looks like it's 540, 541, which, I mean, it looks like that was this point right here, right? But here's another way I can figure that out. This is the midline of the graph at 295, and it's going to go up 246. Well, if it starts in the middle at 295 and it goes up by 246, the highest it's going to get to is 541. What's the radius of the Ferris wheel? Well, isn't the radius of the Ferris wheel like the from the middle to the top or from the middle to the bottom? Don't we have another word for that? We don't call it a radius, but we'd call it the amplitude. Well, the amplitude is just 246 because look, ta-da, there it is. Right, the first number we know is amplitude. How do you find the period? Well, this second number right here, we call that the B value. It itself is not the period, but to find the period, you just do 2 pi, divide by that number, which was like 0.17.
I got 37.
Minutes. It looks like 2 pi divided by
I did,
0.
like, the whole number.
You did the whole number?
Yeah.
I'll do like 1698, I guess. Yeah, 37 minutes. If you had to, what you could do is you could find out this value right here, find this value right here, and then find out how far it is between those two numbers. It's a lot of work, though. The easiest way of doing it is just take your b value, divide it by 2 pi. Okay, last one. When's the radar going to be 100 feet above the ground?
Can't you just go value that?
Not
Or
value
why?
100. Because if you do the value at 100, you're asking him after 100 minutes what's happened. You see how this only goes up to 74 minutes? That's not what we're looking for. We need to make our your y value show up as 100. And I don't know that I'm actually even going to finish solving this, but hopefully you get what to do. Find where it intersects. From right here and right here, that's where he's above 100. Now let's do it. Why not?
I got, for one of them, 40.86.
And the other one I got 33.13. Now, the 40 one right here is probably one he's back up above 100, so we should actually find like this one over here. Does that make sense? But I think I'll just leave that there because you guys can you probably know how to do this by now, right? So find from here to here. That's where he's above 100 feet. Okay. Let me do a quick summary here, and then we can start packing up. So what I need for you guys to be able to do is, for one, you need to be comfortable working in radians. Which, I mean, for the most part, all you got to do is just flip the toggle in your calculator to radians and just understand that rather than going between 0 and 360, you usually are going between, like, say, 0 and 2 pi. But in the context of a word problem, you might even need to change it to, like, 365 because that's how many days are in a year, or maybe 24 because that's how many hours are in a day, something like that. So we typically are going to work with radian values. You need to know how these new 3 properties of a graph affect things. Amplitude is how tall the graph is. That's your first number. Midline is like where the middle of the graph is. That's your last number, your constant term. The number that goes right in front of x, if you divide that from either 360 or 2 pi, that'll tell you your period. Okay. Essentially, if you put a 2 or a 3 or a 4 there, it means that you have more iterations happening. It's happening more frequently. The more frequently it happens, the lower the period. So that's why you take 2 pi and you divide by that number to reduce your period down. Okay. The long and short of it is, I need you guys to be able to solve problems. Okay. You don't have to solve. You know how, like, on that one slide I showed you all the outcomes? Here it was. You don't have to solve. Okay. You have to be able to solve exponents. You have to be able to solve rationals, which is all of our unit 1. You have to be able to use all the log laws, but it doesn't say anything about that for sine. Okay. So all you have to be able to do is look at a graph and solve some problems. I might give you data and you plot it. I might give you an equation. Okay. But pretty much all you have to do here is know the graphs. So that's our unit. Know what polynomial graphs look like, exponent and log graphs and sine graphs look like, and in all of these cases, solve problems involving them. You have to be able to solve exponential equations, like say 2 to the power of x equals 4 to the power of 1. Well, you'd say this is the same thing as like 2 squared. You can cancel the 2's and tell me that x is 2. You guys remember doing that? Or if I said 2 to the power of x equals 4, you could say log base 2 of 4 equals x, and then just type that in your calculator. Or you could even graph and see where they cross. So, yeah, that's our unit. So 4 things: polynomials, exponents, logarithms, sines. Okay. Technically, you can also do cosine. In dash 1, they make us look at a cosine graph. But just so you're aware, a cosine graph does pretty much the exact same thing as a sine graph does. It goes up and down in a wave pattern. So it's possible they might throw cosine at you, but don't freak out about it. It's the same concept. So, any questions? Okay, last thought here then. Here's the plan going forward. You got 2 work days. Tomorrow and tomorrow's Wednesday, right? Wednesday and Thursday we have work days. Please make sure you use them well. If you work hard, you should be able to finish the assignment probably in a class, but I know a few of you are a little behind on that, so make sure you get some help to get caught up, because it's best to do the assignments before you do quizzes. Okay. Friday we're doing another quiz. Monday you're getting a work day, and then Tuesday next week's our unit test. Okay. I'm not assigning any more practice questions in journals it wouldn't hurt you to try some more if you want something to do. But I mean, some of you are behind on that as well. So basically, you've got a week now to kind of finish stuff, whatever that stuff is. Yeah, you got a week to catch up. Sound good?
Sounds great.
All right, we'll see you guys later. By the way, we're here tomorrow again, so come here tomorrow.